Hi everyone, and welcome to the video that I have on concavity and the second derivative test. The objectives for this video are: 1, to determine intervals on which a function is concave upward or concave downward. Number 2, find points of inflection of a graph of a function. And number 3, apply the second derivative test to find relative extrema. The first thing we have to do is to really get an idea on what concavity means. So what we're going to do is we are going to let f be a differentiable function on an open interval I. F is going to be concave upward if f prime is increasing on I, and f of x is concave downward if f prime is decreasing on I. So what's happening on that when the first derivative is actually, as I move from left to right, when the first derivative is going up, I know the function is going to be concave up, and when the first derivative is going down, it's going to be concave down. Now what it means, what it looks like graphically for function f to be concave up, well, what you see right here, this is the graph of f of x. That's a graph of f of x. Here's a graph of f of x over here. Now in this graph over here, this one, f is concave upward. Now notice it kind of looks like it has a feel like it opens to the up. Graphically it opens to up. That's what it means to be concave upward. And in this piece right here, this graph appears to open down, so it is concave downward. So here's another graph that we have, and I want you to notice some things here. First up, as I'm traveling over this part where we're looking at values that are less than c, this portion of the graph would be considered concave downward, and the portion to the right of the c would be concave upward. This point C is called a point of inflection. And a point of inflection is graphically where a function will change concavity. It will go from concave down to concave up, or the other way, concave up to concave down. So wherever we see a change in concavity, that is going to be a point of inflection on our graph of the original function. So how do we test for concavity? Well, what we're going to do is we're going to use the second derivative. We're going to let f of x be a function whose second derivative exists on an open interval I. Okay? The second derivative must exist if we're going to be able to determine anything about concavity. If f double prime of x is greater than 0 for all x and I, then f of x is said to be concave upward on I. If that second derivative is less than 0 for all x and I, then the function is concave downward on I. Make sure you have that, you notice that. If f double prime, if the second derivative of f at x, if it is greater than 0 for all x and I, then I know it's concave upward. If f double prime of x is less than 0 for all x and I, then I know my graph will be concave downward. So to determine concavity is very much like what we did to determine the extreme values, the relative where we had relative max or mins. The first thing I'm going to have to do if I'm going to want to determine concavity is I need to find f double prime of x. Second thing, I need to determine all values of x that will make the second derivative equal 0 or undefined. Those are possible points of inflection. And like we did with the critical numbers we did when we were looking at relative extrema, those possible points of inflection, or the critical numbers of f prime, if you will, will help us identify the intervals where we will test the concavity. It's going to break the domain up into pieces, and each one of those pieces is ones that we have to check the concavity for, see if it's concave up or concave down in that test. And once we identify the intervals, we do want to identify test values, again, like we did last time. And the last thing we want to do is interpret the result. If that second derivative is negative, I know that my function is going to be concave downward. If that second derivative is positive, I know it's concave upward. I also know if when I change from going concave up to concave down or concave down to concave up, I know where I make that switch is also going to be a point of inflection. Let's look at a problem here. The example problem we have is f of x equals x to the fourth minus 8x cubed. And what I want to do is I want to determine when this is concave up, concave down, and I want to determine if I have any points of inflection. So the first thing I need to do, as we talked about, is to find f prime, or the f double prime. So I take the first derivative. When I take the derivative of f, I get 4x cubed minus 24x squared. Now that's the first derivative. I need the second derivative. To find the second derivative, I just repeat the power rule, and I find that f double prime of x is 12x squared minus 48x. Now, remember, I want to identify where this thing equals 0 or is undefined. So what I need to do in this case is I do need to factor that. And I can factor that. There is a common factor of 12x, so I can pull that out. And when I pull the 12x out, I'll be left with x minus 4. So at this time, I know that my second derivative, f double prime of x, is going to equal 0 when x is equal to 0 or 4. Those are the values. Those are possible locations of points of inflection, if I have any. That's where they're going to be. Also, notice on here, again, I'm dealing with a polynomial, so I don't have to worry about the second derivative being undefined. Just like when I have a polynomial, the first and second derivatives will be defined for all real numbers. So I'm not looking at it anything where this could be undefined. Please keep in mind that locations where that second derivative is undefined, those that are elements of the domain, we do need to go through, and those would also be possible points of inflection. So now, what I would like you to do is determine the intervals. We're looking at all real numbers. Our possible points of inflection are at these two values here, 0 and 4. And what I would like you to do, use that information, determine the intervals, and identify a test value for each interval. And then plug that test value into the second derivative and tell me if the function is concave up or concave down on that interval. When you come back, we'll go through what should have happened on this problem. Okay, welcome back. In this case, when we left, we were looking at, we had already identified that the second derivative was 0 when x equals 0 and 4. So that would give us intervals, because we are dealing with a polynomial that's defined over all real numbers. I know that these two values, my possible points of inflection at 0 and 4, will break this up into the real numbers up into 3 intervals. One interval going from negative infinity to 0, another interval going from 0 to 4, and a third interval for going from 4 to infinity. And so when I put those intervals up over here, I came up to this chart that we've been working on, I identify a test value. So these are my test values, right? This is a test value right here on the interval from negative infinity to 0. We're going to use -1. From 0 to 4, I'll use a +1. And from 4 to infinity, I'm just going to pick 5. Okay, those are numbers that are small that are in that test interval, so I'm going to use those. Now, it's important to remember here we are checking the second derivative. So the first thing I'm going to do is I'm going to take this -1 and I'm putting it into the second derivative, in for x. So when I put that -1 in for x, I'll get a negative. 12 times -1 is going to be -12 times a -5. Well, -12 times -5 is going to actually be a positive value, a positive 60. So I know on the interval from negative infinity to 0 that my second derivative is going to be positive, and therefore my function is going to be concave up. Next thing I do is use the number 1, my second test value of 1. When I plug that in for x, I'm going to get 12 times a negative 3, which is going to be a negative 36. So I know that on the interval from 0 to 4, my second derivative is going to be negative, and therefore my function is concave down on that interval from 0 to 4. My last test value is 5. I'm going to plug 5 in for x, and when I do that, I will get a 60 times a positive 1, so I'm going to get a positive number. And so again, on the interval from 4 to infinity, this function will be concave up. So now I've identified what's happening when the function's concave up, concave down. The last thing I really want to be able to do on this one is also identify my points of inflection. And in this case, because we changed concavity at 0, to the left of 0 we're concave up, to the right of 0 we are concave down, I know that we have a point of inflection. There's one point of inflection at x equals 0. And when I put 0 in for x, I do get 0 out. So my point of inflection in that case would be the point 0, 0. And I also have a point of inflection at 4 because I went from concave down to concave up. So I do know I also have a point of inflection at x equals 4. And when I plug 4 into my original function, I get that we have a point of inflection at 4, and it does come out to be negative 256. So keep in mind the process here. This process that we just did on this problem will be the same whether or not you're just trying to determine the concavity of a function on intervals of its domain, subintervals of its domain, or if we're trying to identify the point of inflection. We do have to go through this process and identify where the function's concave up or concave down, and recognize that when we make that switch, it's really identifying the point of inflection. It's just really one more step after this. It's really identifying where we made the switch from concave up to concave down and realizing that that will then identify a point of inflection. Our final thing for this video is the second derivative test for extrema. Now we're going to let f of x be a function such that f prime of c is equal to 0. Please keep in mind it is important that f prime of c equals 0. If f prime of c is undefined, then the second derivative test cannot be applied. We can only use the second derivative test when f prime of c is equal to 0. So we're going to let f be a function such that f prime of c equals 0 and f double prime exists on an open interval containing c. So if f double prime of c is greater than 0, then f has a relative min at c, at the point c, f of c. If, in other words, if where the first derivative is equal to 0, so we know the curve has a smooth curve at that point. If the second derivative is positive, then I know the function that at c, then I know that that curve is concave up at c. So if I'm concave up, okay, if I'm concave up, then I have a minimum at x equals c. If the second derivative of the function evaluated at c is less than 0, then I know the function is concave down at c, and therefore there must be a relative maximum at c f of c. Now, the other thing you have to realize here is if that second derivative equals 0, if the second derivative equals 0 at c, then the test fails. And really, when the test fails, you don't get any information out of it. You cannot come to any conclusion about the function or its behavior. So let's look at an example of a problem here. We're going to use the second derivative test to find all relative extrema for f of x equals negative x cubed plus 7x squared minus 15x. So what I'd like you to do right now, I want you to pause the video. I would like you to go and find the first derivative and then identify the locations where that first derivative is 0. So pause the video right now and identify all the locations, all of our critical values. Welcome back. So when I take that first derivative, we already calculated the first derivative on this. It comes out to be the negative 3x squared plus 14x minus 15. Now what I did to make my life a little bit easier, I did pull out a factor of negative 1. So I have that negative 1 times 3x squared minus 14x plus 15. I just put that out there because it makes it a little bit easier to factor. And because of how this works out, I know that 3x squared minus 14x plus 15 will factor as 3x minus 5 times x minus 3. So f prime of x is negative 1 times 3x minus 5 times the x minus 3. And we then have critical numbers at 5/3 and at x equals 3. So now what we want to do is we want to use the second derivative test. We know that we can use the second derivative test because at each one of these locations, the 5/3 and 3, it does make the first derivative equal 0 and not undefined. So the second derivative test can be applied here. And in this case too, I do need the second derivative, okay? And I know that f prime is negative 3x squared plus 14x minus 5. So I know that f double prime of x is going to equal negative 6x plus 14. And so what I'm going to do now to determine whether or not I have a relative max or a relative min, I'm going to put the values, the 5/3 and the 3 in for x. So what I'd like you to do is pause the video now and plug 5/3 into the second derivative and see what you get. And plug 3 into the second derivative and see what you get. Remember the second derivative test, and I want you to make your conclusion about whether or not we have a relative max at 5/3 or a relative min at 5/3, and the same thing at 3. So pause the video, do your calculations, and do your interpretation, and then we'll finish this up. So in this case, when I plugged in 5/3 into the second derivative, I did come up with a positive 4. Negative 6 times the 5/3 is going to end up being negative 10, because I know 3 will go into negative 6, negative 2 times. So I'll have negative 2 times 5, which gives me negative 10, plus the 14 gives me a positive 4. And I know when I plug plug 3 into the second derivative, I get negative 6 times 3 plus 14, which will be negative 18 plus 14, which is negative 4. Therefore, by the second derivative test, I can say that since we are 0, the first derivative is 0 at 5/3, and since that second derivative is a positive value, I know the function's concave up, and so we have a relative min at x equals 5/3. And since the second derivative is negative 4 at x equals 3, and remember at x equals 3, the first derivative was equal to 0, so the second derivative test applies here. And since it's negative 4 at 3, at x equals 3, I know the function is concave down there, and so we have a relative max at x equals 3. This concludes our video on the second derivative test for relative extrema and on concavity. So what I'd make sure that you take your notes, you feel comfortable with this material, and we will go do a couple more examples in class and then spend some time working on the problems. So have yourself a good evening, and we'll see you at our next class.